Welcome to G Fun Facts Online. Today, we're talking about something straight out of a sci-fi movie that's already on our streets. Autonomous taxis. Forget the futuristic dream. Robotaxis are here, navigating cities like Phoenix and San Francisco. But how do they actually work? How does a car see the world, make decisions, and drive you safely to your destination without a human behind the wheel? We're going to break down the incredible technology, from laser eyes to artificial brains, that makes it all possible. An autonomous car's ability to drive safely comes down to one thing: perceiving its surroundings with superhuman accuracy. It does this with a suite of high-tech sensors. The most famous is LiDAR, which stands for light detection and ranging. Imagine the car sending out millions of laser pulses every second. By measuring how long it takes for those pulses to hit an object and bounce back, it creates a super precise 3D map of everything around it: other cars, pedestrians, even curbs. This 3D point cloud is so detailed that it can tell the difference between a person and a lamppost, and even detect a cyclist's hand signals. But LiDAR isn't perfect. Its performance can suffer in heavy rain or fog, and historically, it's been very expensive. That's where radar comes in. Radar, or radio detection and ranging, uses radio waves instead of light. The huge advantage here is that radio waves slice right through bad weather like rain, snow, and fog, making radar a reliable sentinel when other sensors might struggle. It's also excellent at detecting objects far away and can directly measure how fast they're moving, which is crucial for deciding when to brake or accelerate. The downside? Radar has lower resolution, so it's not great at telling exactly what an object is. Then you have cameras, the eyes of the machine. Just like our eyes, cameras provide rich, high-resolution color video. This is essential for tasks that other sensors can't do, like reading traffic signs and telling the difference between a green, yellow, and red light. They are also much cheaper than LiDAR. But, just like our eyes, they struggle in the dark, with sun glare, and in bad weather. And a single camera has trouble judging distance. So, no single sensor is perfect. The key is something called sensor fusion. The car's computer takes the data from LiDAR, radar, and cameras and fuses it all together, combining the strengths of each one to create a single, comprehensive, 360-degree model of the world. It's a symphony of sensors working in concert to create a picture far more detailed than any human could perceive. Okay, so the car can see. Now what? This is where the brain of the operation takes over, a complex suite of software powered by artificial intelligence. This process has three main parts: perception, decision-making, and control. The perception system is what makes sense of all that sensor data. It uses powerful machine learning models, specifically deep learning neural networks, to identify and classify everything the car sees. These models have been trained on millions of miles of driving data, with humans manually labeling objects. This is a car, this is a pedestrian, this is a stop sign. This allows the system to not just see an object, but to understand what it is, and, crucially, to track its movement and predict what it might do next. Is that pedestrian about to step into the road? Is that car signaling to merge? The perception system figures this out. Once the car has a clear picture of the world, the decision-making and path-planning algorithms kick in. This is where the car decides what to do. It plans its overall route, just like your GPS. But more importantly, it makes immediate behavioral decisions. Should I change lanes, overtake this slow truck, or yield to that cyclist? Then, it calculates the exact steering, acceleration, and braking inputs needed to execute that maneuver smoothly and safely. How does it learn to make these complex decisions? Two words: simulation and reinforcement learning. Before a robotaxi ever drives a single mile on a public road, its software has already driven billions of miles in a hyper-realistic virtual world. In these simulations, Developers can test the car against millions of rare and dangerous edge cases, like a child running out from behind a parked car, scenarios that are too risky to test in the real world. Through a process called reinforcement learning, the AI is rewarded for good driving decisions and penalized for bad ones, allowing it to learn sophisticated driving strategies through trial and error. And this brain is always getting smarter. Through over-the-air software updates, the entire fleet of vehicles can receive improvements overnight, enhancing safety and performance without ever visiting a garage. The race to build these autonomous brains has created a fascinating landscape of competitors, each with a different strategy. First, it helps to know the SAE levels of automation. They range from level 0, which is no automation, to level 5, a car that can drive anywhere, anytime without a human. Most of today's robotaxis operate at level 4, meaning they are fully autonomous, but only within a specific, geo-fenced area. The pioneer here is Waymo, which spun out of Google's self-driving car project. They were the first to launch a fully driverless public service, and they operate in cities like Phoenix and San Francisco. Waymo uses a robust combination of LiDAR, radar, and cameras, believing in the power of sensor fusion. A major competitor was Cruise, backed by General Motors. They were aggressively expanding in complex cities, but their operations were shut down nationwide after a serious incident in San Francisco, where a pedestrian was dragged by one of their vehicles. It was a harsh reminder of the immense safety and regulatory hurdles the industry faces. In China, the dominant player is Baidu with its Apollo Go service. They operate one of the largest robotaxi fleets in the world and have focused heavily on reducing costs, getting their 6th-generation vehicle's price tag below $30,000. Then there's the outlier, Tesla. Led by Elon Musk, Tesla has taken a controversial camera-only approach, rejecting LiDAR entirely. They believe a powerful AI can achieve autonomy with vision alone, similar to a human. It's important to know that their full self-driving feature is currently a Level 2 driver assistance system, meaning the driver must always be paying attention. Finally, there is Zoox, which was acquired by Amazon. They're unique because they designed a vehicle from scratch. It's a symmetrical, bi-directional vehicle with no steering wheel, specifically built for ride-sharing in dense cities. Despite this incredible progress, the road to widespread adoption is full of bumps. Safety is the #1 hurdle. While the goal is to be much safer than human drivers, high-profile accidents have fueled a significant public trust deficit. A recent survey found that 74% of Americans do not trust driverless taxis. The regulatory framework is also a complex patchwork, with different rules in different states and countries. And then there's Mother Nature. Heavy rain, snow, and fog can still blind cameras and LiDAR, and detecting black ice is an incredibly difficult problem that companies are still working to solve. Then there's the famous trolley problem. If an accident is unavoidable, who does the car save? While it's a fascinating ethical debate, many engineers argue it's a distraction. Their goal is to build a system so safe that it never finds itself in such a no-win scenario in the first place. But if these challenges are overcome, the impact on society will be transformative. Millions of jobs for taxi and truck drivers could be displaced, a major societal challenge. But on the other hand, transportation costs could plummet, and by turning wasted driving time into productive time, autonomous travel could add trillions to the global economy. Our cities could be remade. With a fleet of constantly circulating robotaxis, the need for parking, which takes up vast amounts of valuable urban land, would plummet. We could replace parking garages with parks and housing. And because most robotaxi fleets are electric and drive more efficiently, they promise a future with cleaner air and less congestion. So from Leonardo da Vinci's first concept of a self-propelled cart to the AI-powered vehicles navigating our streets today, the journey to autonomy has been long and complex. The technology is a symphony of sensors, software, and artificial intelligence. The path ahead still has its challenges, from safety and regulation to public trust. But the momentum is undeniable. The question is no longer if robotaxis will become a part of our daily lives, but when and how we manage this incredible transition. The future of transportation is already here, and it's driving itself. Thanks for tuning in to G Fun Facts Online.